Is it working? Is it working? Yeah. Okay, guys. Hello, welcome. It's our next talk. And here I would like to present Clint and Paul. And I will tell you something about testing, let's say.
Okay. Yep. Hello. So obviously we are not Monty Taylor. Monty.
He's sad.
Yeah. Monty was on his way here, but he unfortunately had to turn around for personal reasons. So today, myself, Paul, and I've asked Clint to join me on stage because he did a fantastic talk about a Zuul use case yesterday at IBM, and we thought we'd just, rather than doing, if anybody's seen Monty present, it's very hand-wavy and stuff. We thought we'd kind of turn this into more of a discussion, question and answer. So if you have questions, feel free to ask them as we're doing it, rather than waiting to the end, because we have lots of time to get through this, and it seems like a fair bit of people here already know and understand Zuul, and you want a little bit more deep dive into it.
I agree.
So we can kind of skip over this, who am I, because this relates to Monty, but Monty is part of Red Hat. He's in the Office of Technology. His primary mission statement or goal is to work on all things related to Zuul and Ansible. And
who are you, Paul?
so my name is Paul. I also work at Red Hat. I actually had a little thing that I was going to flip over to or not, but I am part of the OpenStack infrastructure team, which is the team that has created Zuul and Nodepool and this testing strategy that we use in OpenStack infrastructure. And Clint, I will let you.
I work for IBM, and if you saw my talk yesterday, thank you for coming. If not, I work on a team that has built an alternative Zuul for testing things using GitHub. So it's kind of a fork that's coming back into Zuul. And previous to that, we actually built a downstream Zuul from OpenStack to deploy our own OpenStack, not a fork, but actually just using Zuul as packaged. And so between the two of us, we have almost as much as is in Monty's head, and it'll come out a lot slower than when it comes out of Monty. So hopefully you guys will be able to absorb it.
So what are we going to talk about? We're going to be talking about Zuul, and we're going to be talking about Ansible. Basically, just by show of hands, is this the first time you're hearing Zuul, the word Zuul? Oh, fantastic. Okay.
And who came in to see a Netflix Zuul presentation? Okay, good. That's not that
Yeah,
Zuul.
because there is technically two Zuuls.
They tried to take the name, but
yeah.
we took it back.
It is a Ghostbusters reference.
Hey, I'm down. Like, we can... Somebody torrent it.
Yeah. So what is Zuul? So at the heart of Zuul, it ultimately is a gatekeeper. And that's ultimately where it gets its name from the movie Ghostbusters. And Zuul is a multi-cloud, scalable, elastic CI/CD engine. And I think one of the coolest things about Zuul is we didn't necessarily set out to create Zuul from day one. It organically grew over the course of OpenStack as a project to solve real problems that we were having with CI and CD and so on and so forth. So the biggest benefit that I think we both agree about Zuul is it has this concept of a future speculative state of your source code, specifically related to Git. And we hope to dive a little bit more into how that actually works. But the idea is we create a fresh VM on an OpenStack cloud. We attach the job to that VM. In this case, version 2.0, we were using Jenkins. So we would have Jenkins initiate code on the remote slave that we would attach to Jenkins. The job would run. All the artifacts and data from that node would be archived off to our log servers and so on and so forth. And then we would actually destroy that Jenkins slave so that we could put it back into the pool of resources and start the whole process again. It does support, go ahead.
Well, the cool part about that is the code that we put on it. So normally, that's nothing new, right? We did that with Jenkins before Zuul.
Yep.
But the cool part was when we started saying, okay, I'm changing this component of OpenStack in response to a change that's still in flight on this part of OpenStack that broke everybody, and in response to a PyPy library that came in, right? And we were able to build a dependency chain, and Zuul actually pulls both in-flight changes in, tests them together, and they land together in each repository. So you're actually able to build cross-repo dependencies, which is actually one of the most interesting features. So you're building a speculative future across repositories and deep, down stacks of commits, which I like that because it encourages you to make small changes.
Yes.
Instead of like, well, I got to package these all together so that I don't have to wait for my gate tests to run 6 times. No, you can have 6 commits. They all run in parallel and they all land at once. That's what I like about it.
Yes, and to that, it definitely is code that is pre-merged into your repos. So the idea is that nothing broken is getting into your master branches because it's gone through this process or pipeline to validate that the test is good, rather than looking at the code and saying, I think it's good, let's merge it, and then your build bots or your build servers start screaming at you because you've broken everything. So some of the terminology. We'll dive a little bit deeper into Zuul. Actually, you know what? There's a really good slide. I'm going to skip ahead here because I think this slide should have been closer to the beginning. So in OpenStack infra, it might be a little bit difficult to see here, but this is Zuul right here in the middle. And you can see everything else that kind of goes around it. So with Zuul being in the middle, it interfaces into Garrett, which is our code review system, which is the interface that our developers use. We have Jenkins over here, and you can see we have 8 of them, 8 Jenkins masters. The way that OpenStack...
Hey, Paul, how many of you think that this is a crazy complicated way to run CI? All right. How many of you know how many developers OpenStack has at any one time? All right. Over 1,000 active developers at all times. Sometimes 2,300, I think, distinct, but there's generally 1,000 developers developing all through this system. 250 commits a day land, pretty much. Sometimes it's up around 400. So we're talking about it. We kind of got ahead of the fact that this was built to scale CI for over 1,000 active developers daily. So yes, that's crazy, but it actually works and it scales really well. So go on, Paul. But I just want to make clear why we did this.
You're right. From an infrastructure point of view, this is my days is managing all of this. But I think if you've ever contributed to OpenStack, your interface is only Garrett. And everything else is kind of hidden from you, except the results, the artifact results that get kicked out at the end, and there's a log stash server, something over here. So when we talk about Zuul, yes, we're talking about one application, but in reality, this is kind of the architecture of it. And it, like Clint said, it's crazy. But this is how we had to scale things out to allow us to run a massive amount of changes at any given time.
As a contrast, the one that we built at IBM, which was downstream from this one, basically testing our deployment code and our small local patches, we had like one Zuul server, one Garrett server, one Jenkins, and one Logstash, right? So it can scale down. We had 70 developers, but we were still actually landing all 250 commits every day in our local repositories and deploying that. So it does elastically contract as well as an application. Part of that's the way that because it organically grew to scale out as microservices, it actually does the right thing and scales back down pretty well as well.
And we'll talk a little bit more into when we talk about Zuul v3, the next iteration, because I think we take it even a little bit farther with the idea of making it less complicated to operate as an ops. So some of the terminology that you're going to probably hear Clint and myself talk about, or anybody who contributes to OpenStack, a periodic job. A periodic job is basically a job that runs on a cron timer. For example, we have a periodic job that runs every 24 hours to build pi packages of everything that we put on our wheel mirrors. Something that we always want to run, don't necessarily care about the job. Well, I shouldn't say that. We care that the job runs, but it's something that we always expect to pass. We have a post
And it's very
job.
expensive.
Yeah, and correct. It is a very expensive process because usually it's a longer running task, maybe like a 3-hour or 4-hour task. A post job, these are kind of inverted backwards. I'll skip down to a check job. So a check job is when somebody submits a patch into our testing infrastructure. You propose a patch using code review. These are the first set of jobs that pass before you actually approve. So as an example for me, I will write a patch and I will throw it up into our code review system for the purposes of having the tests just be run against it. I might throw another 20 patches to that till I get everything running properly. And I'll preface it with something like work in progress, flag it. There's ways to kind of indicate that, hey, this is still kind of experimental.
I have a question for the audience. Any of you use Vagrant? Right? I used to use Vagrant a little bit. I've found that working on OpenStack, I use it less and less because these check jobs are so good. They have enough coverage that basically as soon as I've got something that I think works, I just hit git review. It throws it out into the CI system, and I'm kind of abusing all the cloud capacity OpenStack has. But now when I work on a project that doesn't have that and I have to go back to like Vagrant up and waiting and taxing my laptop, I'm very sad because essentially this exposes thousands of cloud VMs of capacity all at once. But it's kind of the same thing. It's like quick checks, just check my in-flight thing. Is it working? Give me good coverage. And it's more to inform the code reviewers like, yeah, this code doesn't have obvious flaws. So just make sure they didn't change the tests in a stupid way, and then you can read the code and evaluate it on its merits.
Exactly.
That's check jobs.
Yep, and this terminology or technology or concept is not new if you do any sort of CI. Just to speed it up a little bit, a gate job just represents that somebody has actually reviewed the patch and thinks it's well enough to actually be merged. In Garrett, we have a process of an approval, usually requires 2 core reviewers. So I think on average it takes about 2 weeks to kind of go through this process of sign off and approval. And then same thing, 9 times out of 10, the same set of tests run again to ensure that the testing state hasn't changed from the last time you uploaded the patch. And if it takes 2 weeks to actually get somebody to approve it, like a lot, especially in OpenStack, a lot of things have changed. So we rerun the test on approval. If it's green, great, it gets merges in. If it fails for some arbitrary reason, it gets punted back to the developer and you just simply start the process again. And we're gonna show a little demo about that a little further in. And then basically we have a post job, which is jobs that run after code is merged. A primary example is we generate tarballs for every commit for a project. And then we publish them to our tarball server. You want to handle this one?
So I think I talked about a little bit about the massive scale, but I mean, the way that this happened, right, where we got to that giant crazy graph, it started with a few servers in a rack at HP running some tests for OpenStack CI in very boring ways. Just like we're running Jenkins here, and then we have a slave that like builds a directory and then kexecs into it, and hopefully that works. And that obviously didn't scale. So then it was like, well, what if we pointed this at the HP's OpenStack cloud that existed at the time? And then, well, now we need another Jenkins master because Jenkins can only run 100 at a time. And then now we've got 400 active developers and we need 3 Jenkins masters. And now the gate takes so long, we can't wait for, there's 4 approved patches in flight. That's 8 hours because the tests are 2 hours long. And so Jim Blair, who wrote the original Zuul, came up with this idea of what if we built a speculative state where we stacked up all the approved commits and tested them all in parallel across a cloud. And that's where Zuul, that was essentially Zuul 1
Yep.
came out, was just that, the pipeline for the gate. And then we realized this is actually useful for cross-repo dependencies because we're already building up commits. We could do this across repos. So it organically grew with the scale of OpenStack over, I think it's 4 years ago is
Yep.
when it started. And at this point now, it's absolutely the linchpin that holds OpenStack together. I don't think development could proceed in the fashion that it does without it.
Right, and I think one of the great things at the beginning, the people on infrastructure team, Jim and Monty, truly felt that everything had to be automated, everything had to be a robot, because we didn't want to depend on one person. And if you're in a company, works 9 to 5, everybody's in the one office, that's okay. But if you wanted to scale to the scale that OpenStack has contributors worldwide, you don't want somebody in Australia having to wait for somebody in North America to come online to be the guy to push the button.
The sun never sets on the OpenStack empire.
Exactly. I mean, I want to sleep. I'm sure Clint wants to sleep. I'm sure any developer wants to sleep. That's why we write robots, to do all these arbitrary tasks. So now we're kind of getting into some of the scale that we're talking about here. So we've coined a term called KJPH, kilojobs per hour. So we're actually at 2 kilojobs per hour. And what does that mean? Well, that means in a given hour, we're running 2,000 tests. But the cool thing about that is because we launch a VM for every test, we're actually spinning up 2,000 VMs across all of our cloud infrastructure. And I can't remember if the next slide shows what our cloud infrastructure is, but we're up to about 12 regions of capacity across the world. And in those...
Thank you if you donated capacity.
Yes, and this is all donated hardware, mind you. We are grateful that we don't have to pay for any of this. Companies see the value in donating back to the project, and yeah, I don't think we would grow as big as we did, and still are, without companies like this providing these resources. And these VMs are, we standardize on an 8 core VM, 8 gigs of RAM, 80 gig hard drive. So they're pretty, 4 years ago, kind of laptop size because we wanted everything to run on a laptop. So arbitrary developers, these stats are a little bit older, but yeah, like 2,400 developers at any kind of given time writing code.
That's actually peak.
Yeah.
It's generally around 900. It peaks in the cycle at 2,400.
Yes. I'm sorry, yes. I didn't, yeah.
These are just the biggest numbers we have. Why would we show you the smallest?
We're up to about 1,500 Git repos that we manage. Jobs, and these are, if people know what JJB is, Jenkins Job Builder, these are, once we have Jenkins Job Builder create all of our jobs, we're pushing about 12K worth of job definitions and so on and so forth.
I will say Zuul v3 should reduce that. A lot of those are distinct just so that they have a different name. Yep. Because there's a quirk to the way Zuul creates shared queues that they need to have a different name or they'll get co-gated. So I think v3 will take that down to, I think, 3,000, which is still a lot of jobs. But part of that is just naming. And
about 10,000 changes per month that we merge. So just as a comparison, the Ansible project has about 14,000 pull requests in its lifetime. It's merged about 8,100 commits. Oh, I'm sorry. It's merged about 8,100 of them, and there's close to 40,000 commits. So, the scale is just massive.
So in 4 months, OpenStack makes another Ansible. Every 4 months.
Yeah. So multi-repo speculative execution. So this is what Clint was referring to.
Good time for the demo.
Yeah, I think what I'd like to show first is the demo of how all this works, because
not a demo really, but it's a fantastic animation.
Simulation.
So that we don't have to wave our hands so much. Watch as Zuul handles your commit.
So again, we have a concept of a pipeline, which if you've done CI or you've talked of CI, you hear the word pipeline more and more these days.
The tiny text there, by the way, the blue dot says Nova, and the yellow dot has a head for Keystone. So Nova and Keystone, if you're not familiar, are two different OpenStack projects that are co-gated. So they both have to pass for either one to land a commit.
Yeah, what we're showing here is a parallel co-gating pipeline in Zuul, where both, exactly right, Nova and Keystone are interdependent on each other, but different repos.
Yeah, and then above there you have 4 changes that have been approved, 3 to Nova, 1 to Keystone. The idea is that Nova can't land a commit that breaks Keystone, Keystone can't land a commit that breaks Nova.
Yeah, exactly right. What we're showing here is 4 patches are online. Sorry. I got to click here. So four patches have come online, and they're being queued up into Zuul. So the idea is that Nova 1 is basically in the speculative state applied to the master, the tip of Nova. It runs its set of jobs independently. The second patch set applies the previous patch set 1 and master and launches its set of testing. And it continues down. Keystone does the same thing, queues up the previous patches and 4. So what's actually happening is, as somebody approved all of these simultaneously, we are going out to the cloud and we're running these speculative tests in parallel across all of our testing infrastructure. And because Zuul knows the future states based on this history, it can do some really cool things.
Yeah, so if you count the lines there, they're a little small. There's 15 parallel jobs running all at one time. And the first 8 have passed, and then one of the Keystone jobs has failed, which is why it's gone red. And then the Nova one has also failed because it's stacked on the bad commit in Keystone, so that the rest of the queue has basically failed.
So we have a question.
The ordering is determined just by when they were approved.
It's just in queued order, unless there is an explicit dependency. So the Nova ones are in the same repository. So if they were stacked on each other, then there is an imposed order. But and also if there was a cross-repo dependency imposed, right, then there would also be an order. But otherwise, it's just how they were in queued.
So in this case, if the Keystone patch requires the Nova 4, and if by accident they have switched timestamps, then it will fail.
So the question is, Keystone 3, I'm sorry, Nova 4 requires Keystone 3. Okay, I'm sorry. So Keystone 3 requires Nova 4. So,
But it was not expressed.
but it was not expressed, it would fail. So yeah, you're right. In this example, it could be that is the reason why it failed.
In this example, that didn't happen, though, because 4 failed as well. If that was true, 4 would have actually passed, because it would have everything it needs. So that's not what happened here. But if you saw green there, which could happen and does happen, what would happen is the Keystone commit would get kicked out.
Well, hold
and
on.
the Nova one, oh God, go ahead.
So I think to answer your question a little bit more, so for 1 and 2 are good, Zuul is going to merge those. 3 and 4 are bad. 4 may have been canceled or it had job fails. So Zuul is smart enough not to kick 4 out because it has a failure ahead of it. So it's going to move 3 out of the pipeline. Let me click this again. Kind of moves it out of the way. And then it rebases 4 atop of 2. And it does the tests again. And as a developer, this is kind of invisible to you. You don't have to do this. Zuul kind of takes care of that. And then what Zuul is hoping is that when 4 runs again, it's going to pass because it truly isn't dependent on 3. And then what happens is 3 continues to run. You can see, I don't know if it shows it up here, but 3 will eventually continue running. Even though 1 job has failed, we will run the whole suite of jobs so that we present as much data back to the developer.
Correct.
So number 1 is green. We passed all of our jobs. So Zuul merges into Nova. 2 is great. It's green. Again, gets merged in. 3 we know is bad. We kick it back to Garrett. We leave a message indicating log failure, so on and so forth. 4 is green. It gets merged in. And the beauty part is nobody had to
Zero
merge
humans.
this code. It was all robots. Question?
So, if they're codependent, in theory, number 2 could have been an API change.
Right.
So 1, 2, and 4 could have been great, but number 2 was an API change, not number 2 compatible, which no developer would ever do. Why would you take that in? You're effectively broken Keystone forever.
Let me read the question back real quick.
Yep.
So what you're asking is, if in number 2, which passed its tests, we may have actually broken the ones after it. They are.
Only broke Keystone because they're in 2 different repositories, as I understand your simulation. So Nova should continue to work with its own repository, but you made an API breakage effect.
Right, so we may have broken the API for Keystone. Yes, that's a possibility. It's not actually what we're trying to cover in this simulation, but that's an absolute common thing that happens in any distributed system, right, where things are passing all the tests, but then the next thing adds a test that the last commit broke. You would hope, we didn't just run the Nova tests to get that green. We ran the OpenStack Tempest test suite, which tests all of OpenStack. So it tested Keystone. We didn't just run Nova's tests. So
Yeah.
Keystone's test passed on 2. One would hope that we didn't break Keystone. And that is an important part of having a good integration story, cross-repository integration, is make sure you're running all the tests on all the things that are co-gated together. We have made that mistake before, where one is not running the test and one is, and one of them keeps breaking the other. That was actually a very early problem that was solved mostly just through socializing the fact that you can't be co-gated without running all the tests.
So this is something that you get in Zuul out of box, okay? I think we can continue on here.
Does everybody understand this idea of a speculative future that we just displayed there? I want to make sure, because it's, I think, the coolest part of Zuul, the idea that Zuul as a robot creates a pipeline of changes that are in flight and lands them all in parallel. Yep, in the back.
You have 1,400 repos. You have integration tests. I'm assuming those. You don't test every, or you don't retest all the changes. You just run those integration tests that you have on every change. So if you have like 10,000 sort of independent projects or codependent projects, you want to use Zuul to test that you don't like exponentially make the matrix bigger.
So the question is, we have 1,400 or so repos. Do we test the entire matrix of combinations together? Absolutely not. I can't do the arithmetic in my head, but that matrix would be insane. No, that's just the number of distinct repos. They're essentially testing islands in OpenStack. So there's what a lot of people referred to early on as the integrated gate, which was basically the core of OpenStack, and I think that was 16 repositories at its biggest size, and I think it's actually been pared down a bit. That's probably the biggest co-gating matrix, and I think that runs maybe 20 different jobs to test the different combinations of common configurations. So let's make sure it works with Postgres and MySQL and this driver that's common in this one, but it still doesn't test the entire matrix. That would just be too hard.
So I'm making an assumption that developers can optionally include the dependency information in their common message to indicate this full dependency.
Yeah, so the follow-up question is, can developers just arbitrarily state dependencies in their commit message? They absolutely can, and an important thing is they can state dependencies on things that are not co-gated to them, and that's fine. That means your project is taking responsibility to follow that one. That project doesn't have to care that you depend on them. Doesn't have to. So it can be a one-way or it can be a two-way dependency. That's actually more of a social problem than a technology problem.
Yeah, I was exactly going to say that. I think it's a social contract between projects, because I think the next slide kind of gets into this. So, and I think it's going to address your question, is how to force a dependency is we've created a depends on header. So as an example, I'm going to kick to the next slide, but I just wanted to highlight this is how you express it in your git commit message. This is the change ID that's generated by Garrett. This is the change ID of another patch in Garrett. So an example, OpenStack has a shade library. For the purpose of our discussion, it is a wrapper around all of the OpenStack API, Python APIs. We run tests against that for OpenStack. Now, Neutron, which is our networking project, creates a breaking change for shade. Neutron proposes a fix. Shade then depends on that patch because there isn't an explicit integration gate. Like the social contract is Shade sees value in testing against Neutron. Neutron doesn't want to depend on Shade's testing, right? So Shade expresses we need that fix to fix us. Shade's tests all run as if Neutron has landed that, and Shade basically says to Neutron, this is good, but we can't merge this code until Neutron finishes its process. And that is the way that Zuul expresses itself so that you don't put what is the expression? The egg before the chicken or something like that, right? So that's the whole concept of the cross-repo dependency of not having, I guess, this integrated queue.
I'm not sure we ever solved that chicken or egg thing.
Yeah.
So I think the cart before the horse.
Maybe that's what it is.
But it is the idea there that the ordering is up to each patch developer, not each project.
So I think
and just to expand on that, at IBM, when we brought this functionality to our developers who had never had anything like it, it kind of blew their minds because they were used to having to harass developers to make releases of things so they could depend on them. And it was like, no, you can't make your release until it lands, but you can finish your development and you still have your green passing test, and just when it lands, they both land and magic happens. And it became this nice, like, I can get that change out of my head. And it's actually the main reason we started the Bonnie CI project I talked about yesterday, was we want to bring that to everybody. And that's actually also why Zuul v3 is happening and trying to bring it to Ansible and things like that. Is I think this is going to help open source developers get things off their plate faster.
So yeah, so basically just to follow up, but isn't Shade supposed to prevent Neutron from breaking? Again, it goes back to the social contract. Shade cares about, maybe cares is a bad word, but Shade needs Neutron to function. Neutron doesn't need Shade to function. So it's the one-way dependency. And something like this, if Neutron breaks Shade is willing to accept that risk and be the project to react to those breakages. So again, not specific to OpenStack. Gate and check pipelines, they're just arbitrary words. In theory, you could have a pipeline, so when somebody uploads a patch, you could have this multi-process pipeline where it just continuously grows testing after each pipeline before it, to scale out your testing that way. We have about 50 plus vendors that are actually using Zuul because the way that we do third-party testing, in the case of Cinder, for example, IBM might have a driver that they want to test in-house on IBM hardware. They would set something up in their corporate firewall because they don't want to expose that hardware to the public web. Every time Zuul comes in and detects a change set, Clint's version of Zuul listens to that event stream, kicks off its testing, and then reports back upstream. So it truly gets us into a not only distributed testing, but distributed results testing, I guess is maybe the word. It's super powerful. So now you don't need to cram all this hardware into one ops center or one team. Again, a social contract is there to allow IBM to post results, but if IBM's system stops working or goes rogue or something like that, then we politely ask them to turn it off. If they don't, we cut them off. Things like this, right?
Yeah, the key there is there's a one Garrett to many Zuuls relationship, which actually ends up being powerful even within organizations as well. As while we were doing the IBM cloud thing, we did have another organization spin up a third party and start testing their driver with our cloud, with their Zuul, the same one that would test upstream, which was actually a pretty cool thing to see.
So I just got the 10-minute warning, so we might have to
hop to it.
Yep. So Wikimedia, for example, is somebody who uses Zuul. If I'm online, this is what their interface is. Just a quick point. On Friday, they pushed almost 1,000 kilojobs. It's awesome. They've really embraced Zuul and Node Pool and so on and so forth. This is our representation. You can see we actually have things in the check gate right now. If I drill into, hopefully I can find one with a good IP. I don't know if I'm going to be online or not, but these are the tests that are actually being run. If you were to click on this link, it would take you over to Jenkins if we were still running Jenkins, because we don't run it. That's the next part we're going to talk about. But yeah, all of these individual tests are spinning up VMs. And because we have something called Node Pool that does it for us automatically, no humans involved until something breaks. But these are our statistics down here. So you can see Wikimedia probably beat us, I think. No, maybe not. This is only over a 12-hour period. But right now...
It's also Saturday.
Yeah, it's also Saturday. Yesterday, if you looked at Clint's presentation, the check or the gate queue here was totally packed with like 40 or 50 commits. And because Zuul was doing its thing, no humans were waiting. It's a waiting game till all the tests are run and so on. Okay, so let's kind of skip over some of that. So basically, Zuul 2, what it got us, 4 years of running in production. It's what most people run today. Basically, triggers are Garrett and periodic. Publishers or reporters, again, are report back to Garrett, email, MySQL. Node provisions are static and elastic. Static means we depend on Jenkins to create them. Elastic is we use Node Pool, and our jobs are executed by Jenkins.
Most of the third-party CI, for instance, just they have a couple of servers hooked up to whatever special hardware they're testing. They don't need a Node Pool with a giant cloud behind it.
Yep, so that got us to this complicated design, which we showed at the beginning. So 2.5, this is what we're running today. So basically, we replaced Jenkins with Ansible. And our jobs are actually, we still use JJB, but on the fly, we convert those jobs into Ansible playbooks.
Anybody using Jenkins Job Builder, by the way? It's actually pretty awesome, right? And I think it actually gets lost that it actually came from the infra team at OpenStack, but it has become pretty popular. I love it.
Yeah, it's a way of expressing Jenkins jobs in YAML and then converting them on the fly into XML and pushing them into the web interface. So you can code review your jobs and not touch the web interface of Jenkins. Because remember, we had eight interfaces, and that would be problematic. So, so basically, this is what a configuration of a job looks like. This is actual live job that ran this morning. So this would be the playbook that I got kicked off the Wi-Fi, off the Duo. Yeah, but anyways, it would express a playbook and so on and so forth. Okay.
But why replace Jenkins, Paul?
So, yeah, it wasn't for lack of trying. So that big massive diagram was basically all to support still using Jenkins. We started with Jenkins. Actually, I think it was Hudson was the original. Then we, went into Jenkins.
Anybody else run Hudson before it was Jenkins? Right on.
Yep.
Represent.
So we as the OpenStack Infra project, we've maintained various plugins. A JCloud plugin, basically a Garrett trigger plugin. We had SCP artifacts plugins. We wrote Jenkins Job Builder, which we just talked about before. A Gearman worker like Clark built that. 5 minutes. Oh man, we're running out of time here. Basically, we tried everything to get it going, and unfortunately, we just couldn't top out more than 1,000. So there actually was an actual reason why we did this, but before we get to that, we just want to acknowledge that the world would be is a better place because of Jenkins and the CI that it's brought. It's just unfortunate that at the scale that we as a project were working at, it didn't fit our model.
But respect.
Yeah. So, Clint.
Yeah, so the basically what happened is we ran into a security flaw that was pretty serious. And OpenStack was running one of the biggest public Jenkins in the world, and we had to shut it down and turn it off. We couldn't expose Jenkins Web for a while. And after stacking all of those workarounds on top, the infra team looked at what Jenkins was actually doing for us, and it was at that point mostly SSHing into things and displaying text on the web. Everything else was being done by Zuul and Jenkins Job Builder and all the tools that we built around it. And so the idea was, what if we just took Jenkins out and replaced it with a few lines of Ansible?
And in fact, we know a better remote executor, right? And that's basically Ansible. So I know time is short, but basically what we did was we blew out this part here. This is the previous Jenkins masters, which we've turned into Zuul launchers, which at the heart of it are Ansible playbooks. And we have a process that starts everything else up to this point of the node generation and so on and so forth is still the same, except when we said, Jenkins, build me something, we said, Ansible playbook, run me this at this port, this SSH port.
It actually still speaks the same Gearman plugin protocol that Jenkins does.
Yep.
So it's pretending to be Jenkins, but it's actually just a box running Ansible.
Yep. So that's ultimately what 2.5 gets us today, right? What we want is Zuul 3, and I think we're going to run out of time on this one here. But basically, Zuul 3 is everything that we would want if we were to sit down and design this properly, not necessarily let it grow organically and so on and so forth. So basically what we're doing is, because 50 or so people are now running the version 2 of Zuul, we're like, wouldn't it be fantastic if other projects could run this? So we're looking at it as other projects outside of OpenStack are really going to be, we're hoping, going to utilize this. And because we as OpenStack Infra make a lot of specific assertions of how we do things, may not translate to what you want to do. As an example, we love OpenStack clouds. We love running on OpenStack clouds. You may not have an OpenStack cloud and you want to do bare metal testing, or you want to do containers, or some sort of other thing that I can't even think of.
Kubernetes thing that people want to use.
Yep. So the concept is those are going to be considered first-class citizens. AWS, Google Cloud, those are no longer bad terms. That.
I mean, just to kind of try and wrap it in a bow, think of Zuul version 2 as an internal project that's kind of gotten loose, and V3 is an attempt to rein it in and say, no, we're actually going to take care of this and make some guarantees about it. So the infra team is like, well, we'll support V2 for these limited third-party use cases, but then Wikimedia runs off and runs a giant amount of stuff on it, and it's like, well, we don't really know how that's going to operate. We didn't design it for you. We designed it for us. Yep. V3 is actually designed with a proper public API sort of thing. So it has some guarantees and some things that you would need if you don't want to run at OpenStack scale. Question. That is a very good question. Is OpenStack an internal project that got loose? Perhaps.
So
ask the boys at NASA.
We're getting 1 minute here. So that's with questions afterwards, right? Or, okay. So we got 1 minute left. Does anybody have questions, or do you want us to keep kind of talking here and propose questions? When's V3? That's a really good question.
The hope is for March.
Yep.
So we've been working on it for a while this year. The reality is probably more like June. I mean, it's getting close. March is probably when infra will start to run it.
Yes.
But it's probably also going to be a little ugly and rough. So there's a big sprint at the end of February, the OpenStack project team gathering, where we're all going to be in one place and we can pair up and kind of push it, over the hill. Beyond that, Yeah, I have a project that's waiting on it as well. So we want it to be done as soon as possible.
Yep.
It is a pretty steep learning curve, but if you want to join the development effort, you have some Python skills. Hashtag #Zuul.
Yep. Pound Zuul.
Yeah, pound Zuul on Freenode.
So I just wanted to highlight one of the big things that Zuul v3 kind of addresses is we're good at CIing projects. We're not necessarily good at CIing Zuul. So configuration changes to Zuul today are really human-approved processes, which end up blocking projects.
It's centralized.
Yeah, it's server-side, requires a root admin to say, yes, this looks good, or I think it looks good, but we have no way of testing it, right? So
the irony is that it's really hard to test the changes to your tests.
Yep.
Which is really annoying.
So everything is going to be in repo now. Again, Zuul starts very basic, learns its configuration. As a proposed patch is uploaded, if it contains a change to this configuration file, it goes out to the mergers, asks for everything again, rebuilds it all, and then again, pre-commit, runs all of these things again, and inherits all the functionality it depends on, cross-repo dependencies, and so on and so forth. And basically, the concept is test your tests before you land them. That's really what we're aiming for now.
Anybody use Travis? Travis CI? Right? Works more like that. So you have a file in your repo that defines the matrix of tests that you want to run for your project. And then you are only constrained by the Zuul admin at what those can do.
Yep. And then basically true first-class multi-node support. We were kind of mentioning this before. We could say, give us a controller that's Ubuntu. Give me a database server that's CentOS. Whatever, like the possibilities are endless. Today, it's give me 3 nodes, and those 3 nodes are CentOS. And it's kind of limiting. And then again, these are basically node pool changes. We kind of touched on it. We're wanting to add container support, Kubernetes support, bare metal support, any other thing that you want. It really is going to be a pluggable infrastructure to drop in and support that. It would be basically writing a driver to what your thing is at the end. And yeah, so this is kind of answers the question. Status is focus on OpenStack first. We're hoping in the next few months to get it into OpenStack, I think by March. So we can churn on this, fix everything, and then masses come in. And ultimately, the next step is to actually get the Ansible project on it using the Git interface. So instead of using Garrett, we would use GitHub, pull requests, and so on and so forth, and get all the fantastic support that Zuul does today.
And hopefully Bonnie CI will also be using it.
Yep.
This is my project.
And that's it. So this is more information. Again, I encourage everybody who is actually interested in Zuul v3 to read this specification because it goes into more technical detail of some of these structures of what an in-tree configuration looks like, what we are trying to accomplish. We're depending on Zookeeper, all these good things.
You have like basically 1 minute for questions.
When are you going to replace Nova by Zuul?
Sorry, say that again?
When are you going to replace Nova by Zuul?
Nova by, so the question is, when are we going to replace Nova with Zuul?
I'm sure somebody's already done that in Go.
So hopefully everybody found this. So who's going to go and run a Zuul now because it's awesome?
You get a Zuul, and you get a Zuul.
Zuul's for everybody. But yeah, hopefully you found it informative. Definitely talk to Clint, definitely talk to myself, or just jump into OpenStack, Infra, or pound Zuul. Lots of great people.
And again, sorry, we're not Monty.
Yep. If you find Monty, pin him down because he would love to talk about it.
Thanks so much.
Thank you. Yeah, I think it went pretty good.
And the thing is, we can actually have additional metadata, right? The
lock-in dependencies, which could help with speculative automation. And I wonder
Right
something
now you're
that,
expressing you have like a build dependency of a version.
yeah,
And this would change that, and then you would still do that, but you might also express the commit at which that version, the actual change of that repo is.
right.
So you could tell people there's testing from the release of packages, which is actually an important part of being able to move development faster. Like releases are important for people that you don't have control of. But when you actually control this repo, you can just use PRID or a change number or shop, whatever it is, and then it will stay. So that Monty and I have talked about your use case for it as well.
Additional, yeah, I know Ralph Bean has been talking to Monty.
Essentially, that metadata is for when the source package is released.
Yeah.
We want to get ahead of that and put it up in the commit message, which is sort of metadata to the metadata.
Sure.
Saying I think it's dependent on that one.
Well,
Right.
in a lot of cases we know, right? It's expressed,
Yeah.
and like making use of additional information to not have to do weird stuff with 20,000 repos.
Yeah.
Because like 1,400 is okay, but it's not going to be enough for Fedora. We
Yeah.
would like to. On the other hand,
There's
like,
no reason
yeah,
you can't do 50,000 repositories.
sure.
Because once you've gotten past about 200, you have to have a scale-out merging service, which it does. So I think OpenStack runs 15 mergers, which are just VMs somewhere. So Fedora might run 50.
Right.
But the
I
thing
guess
is,
the problem is keeping the costs reasonable.
the thing is, it's how many things are you going to co-gate together? Are you going to try to do the whole history? Like you might need 128 gigs of RAM to run Zuul on, just because keeping the graph of 20,000 repositories potentially.
Right.
Like one change will be fine, but when the dependency chain goes really deep, like right now, if I make a change that depends on 15 other changes, it'll take 5 minutes to merge, just because it has to ask Garrett so many times, like, is that change independent of it? It has to dive down commit messages and things like that.
And that was the reason why I was asking. Like,
Right.
maybe we can like simplify the tree by just looking at those like build and runtime dependency repos.
Yeah,
not
I don't
every-
think it'll actually, you still have to build the tree. That's it. Once you have to build the tree in Python, in memory, it is going to become a graph problem. And that is one area where 20,000 co-gated repositories is probably going to require some rework.
Yeah.
Basically, right now your scheduler is a single process, and you would have to have a scale-out graph scheduler.
Well,
Actually, I mentioned this early on in Zuul. The right answer for that is a graph database. Neo4j is great. It's available. It works. And if you did it in Neo4j instead of in memory, it would actually be faster for even the 1,400 repos. So that's probably where it would go. Join us. But unfortunately, that's cart before the horse. V3 needs to get done.
yes.
Because you also definitely want a repo configuration for package management. Right, because it's like a package is kind of like the maintainer's need to know.
Right.
You don't want to have to go to a central repository.
Ideally, I think we'll need to have both some automated way and then those manual like okay, I know I'm dependent on something, but even if you're not realizing you're dependent on something or you're breaking someone else,
It might be cool if there's a way to detect it, especially if you're just depending on an already released. That might be easy.
there is another point where you have layered products. Like, what if a change in the packaging rel breaks?
Yeah, it's those upper bounds too that get you right. And the new one breaks me. We fight that in OpenStack by having a centralized dependency repository that controls the upper and lower bounds.
Okay.
But because we've hit that, absolutely. The new version of setup tools breaks half the projects, so we have to just cap it off at a project-wide level and kind of override all their requirements files. And then basically we fail every test and say you need to update.
Okay. Well, I mean,
Yeah.
solutions.
These are actually